Thank you very much. So first of all, I would like to thank Omolulu, Franco, the organizers for the kind invitation. I'm really glad to be here. So I thank most people being present in Kigali and connected on Zoom. And so my talk will be about dissipative many-body systems, and I will try to motivate the presentation. So the message is essentially that quantum information, then you can do something useful also using an external environment. So people, I mean, typically one thing that, you know, external environment is always a disaster for quantum information protocols. So I will try to motivate the fact that in some cases actually it is helpful. So I don't know how much it will take me to give the introduction. So let me first just acknowledge the people with whom I collaborated on these talks. They are spread all over the various continents. There are people in Europe. I'm collaborating with Marcello Del Monte, who gave a talk, I think yesterday or 2 days ago. Marco Schiro in France, and Jonathan Keeling in St. Andrews. But I mean, the topic that I would like to cover, I really worked a lot with Fernando Iemini, people in Naples, and also with Sai Vinjanampati and his student in India, and with Michal Yadushek in Japan. So I will try to give quite long introduction, but and so my idea would be just to cover the work is listed in these papers, but I'm not sure I will manage to do so. So let me start by introducing the question I would like to study. I mean, it's about quantum simulators. You already heard several times, I mean, the usefulness of quantum simulators. And so these are quantum many-body systems. They are artificial in the sense that you just fabricate by any means or another. Just the previous talk, we heard about photonic implementation, but you can use trapped ions, atoms, optical lattices, solid state, whatever. I mean, there are really an enormous variety of ways to realize this systems which can be controlled. And the idea is that, and we showed just in the previous talk an example of this, the idea is that by realizing the system that you really can manipulate at your will, then you can test essentially models of condensed matter or other many-body or complex systems you are interested in that are hard to understand otherwise. I really would like to stress the fact that you test the model, you don't test the system. So when you study superconductivity, high temperature superconductivity with a quantum simulator, what you do is just to test if by implementing the Hamiltonian of Hubbard model, you just test to which extent Hubbard model is a good model for high temperature superconductivity. So we are talking about Hamiltonian engineering. Now, in Hamiltonian engineering, there is some echo or something. No, it's off.
What about your sound?
It's off. Everything is off.
Then it's not you.
I don't know. I think it's off. I just did it previously here. You see, this is it's off. Okay. So if you are aiming at realizing or engineering an Hamiltonian, then obviously you want the system to evolve coherently as much as possible. And in this sense, the external environment is the devil. So you really want to get rid of this. But now I come to the main question of my talk, that is it possible to use the environment? So instead of doing Hamiltonian engineering, you try to manipulate to the best that you can and to engineer the environment in a way that is useful to perform quantum information protocols. So if the question is, or the statement is, if it's possible to have access to certain properties of the environment, then actually it will become a resource for information protocols. So, I mean, there are many, many works on this, and I think at the level of few body system, this has been discussed much earlier, but I will start from these two papers that appeared slightly more than 10 years ago that really looked at the many body context. The work by Verstraete, Wolf, and Sirac consider really the power of dissipative processes in terms of the ability to do computation. And actually they proved that if you take a system which evolves with Lindblad type of dynamics, only dissipative, as long as you are able to design the Lindblad, I mean, the dissipative dynamics, I will tell you a little bit more in a sec, then essentially by waiting long enough in the steady state, you will reach the result of computation in an equivalent form as any other model of or approach of quantum computation. So if you do quantum computation with gates, single bit and 2 qubits, then you have to write down a sequence of gates. The same way, they show that you can construct a master equation whose steady state is unique, and it encodes the outcome of the circuit. There is another aspect that I would like to concentrate here in this talk, and it was discussed in this work by Sebastian Diel and co-workers. That is, dissipative processes offer also a route to prepare many body states. You can prepare many body states, but just adiabatic dragging, changing the Hamiltonian. So you start with a simple state. I don't know. You just take an Hamiltonian which has a magnetic field plus some interaction, and you really want to construct a certain complex interacting ground state. So adiabatic theorem tells you that if you start with all the spin up and the Hamiltonian is the it's just a single particle magnetic field, and this is the ground state. By just switching on gradually interaction, then you can reach the desired ground state. Of course, there are complications. In part, we heard about Kibble-Zurek. I mean, this procedure might be complicated if the various ground states are kind of separated by critical point. Sebastian Dill and others that show that actually in the same way in which you can do Hamiltonian engineering, you can do reservoir engineering to prepare many body states. So you just design the interaction, the interaction to the bath, yes, and that's it. You just wait for some time, and in the steady state, you get the desired quantum state. So this is what I would like to concentrate on this, and in particular, just want to show that you can get also some strange or exotic state that I will tell you about. So if you have a generic system, which is described by, which is governed by an Hamiltonian H and coupled to the external environment, then this is the equation of motion for the density matrix. And on very general terms, the part, the L of rho, which is the one associated with the coupling to the environment, has this celebrated Lindblad form. So all the equation is boils down in understanding how to choose or how to design the operator L, this in such a way that if you reach the steady state, you will get a many body desired state. In this type of dynamics, the steady state will be reached by kind of competition between the unitary part, which is the Hamiltonian, and the dissipative part, which is this calligraphic L. So deciding how to reach a given desired steady state means, first of all, a choice of the Lindblad operators to the best that we can, but also choose the presence or not of the Hamiltonian, which will affect the interaction. Now, in the same way in which Kibble-Zurek mechanism may slow down the preparation of many body states by adiabatic evolution of Hamiltonian, here there are issues related to the spectrum of this linear operator. So the spectrum will have eigenvalues which are complex, the real part which will give the decay. So there will be one steady state plus other states that will decay. Now, how or when to reach the steady state will also depend on the spectrum of this Lindbladian, and this is not a trivial task in many body case. Just one example that was discussed soon after the work on the initial work. Again, by the same group of people, more or less the same group of people. That is how to prepare a key-type, the ground state of a key-type chain. So it's a topological state. So how to do it? Well, they showed that if you take a purely dissipative system, zero Hamiltonian, but you choose, and they have proposal on how to implement it in optical lattices. If you choose the Lindblad operators in such a form, so it involves two sides, so you have one-dimensional systems, and you have dissipation, which is kind of related to two neighboring sites. It's number conserving, so the number of fermions does not change in time. Then what you can show is that the steady state of this dynamics coincides with the ground state of the one-dimensional key-type model. So this was a first example on how to see that topology can be generated by a dissipative mechanism. Now, in this spirit, I would like to address another possibility that we have been studying for some time. That is kind of dissipative preparation of time crystals. So what are time crystals? So let me give you a fast intro to the topic. Frank Wilczek introduced this terminology together with the problem exactly 10 years ago. So he said, okay, I have a system. I mean, can be either classical or quantum, but we will talk about quantum. Is it possible to have a situation in which time translational invariance is spontaneously broken? So if I have space translational invariant, which is spontaneously broken, this is just a crystal. So if I have a transition between a liquid and a crystal, it's space translation which is broken. What happened, or if it's possible, and what happened when time translation is broken? In the same spirit, he said, okay, let's call this phase, if it exists, a time crystal. This phase exists, and the first, I mean, there is a lot of history associated with this, so I will not, I have no time to go through it. But one important point is that there is no, I mean, besides the name, there is no analogy between space crystals and time crystals. This is very important. Space crystals are equilibrium state of matter. So equilibrium thermodynamics applies and all what we know. It was shown by, in a very important paper by I forgot the names, of Oshikawa and Watanabe, I think, that time crystals can exist, but they cannot exist in equilibrium. So this is a purely non-equilibrium phenomena. And the first experimental demonstration of time crystals came in two papers in 2017, following by theory proposal 1 year earlier by two groups that say, okay, a simple way to realize non-equilibrium, non-trivial steady state, but just applying a time-dependent periodic Hamiltonian. And these time crystals were named Floquet time crystals. I mean, there are a lot of subtleties, but essentially what happens is that you apply a periodic Hamiltonian of period t, and the system will respond by a frequency which is half of the driving frequency. So it's period doubling. It's a kind of many body period doubling which occurs, but it is emerging from the collective behavior of the system. So again, here there was a lot of, well, not a lot, but there was some discussion about the role of the environment, because in these Floquet time crystals, it is important to have a coherent dynamics. Well, actually, it turns out that this type of time crystals can occur also in many body open systems. In this sense, it's a kind of preparation of these states. And in the same way in which, so what happened is that you have a many body system coupled to a bath, and the steady state stops being a single steady state, but the system enters spontaneously in a limit cycle. And there are some analogies to kind of synchronization that if I have time, I may comment. I mean, there is some delay. Okay, now it's here. So there's been quite a lot of work, and this time crystal in dissipative systems were studied in several different contexts, realization, and so this year, the first paper appeared reporting on experimental observation of this many body limit cycle in a kind of dissipative atom cavity system. And the limit cycle that they observe are in the oscillation of the photon number. So I really would like to, so I will not talk about this, the experiments, but just give you a flavor of how this can be realized by considering a simple model, essentially because it's the model where I work on, and but I mean, there are, as I said, many other examples of this sort. So it's a simple model in which there are spins on a lattice. They are independent, so the Hamiltonian is just a magnetic field along X, but the interaction is appearing in the coupling to the environment. So while the Hamiltonian is a trivial precession of each spin, the decay is a collective decay. So you see that the Lindblad operator is the sum over all the spins. And it's pointing down. So they try to flip the spin down in a collective way. So this is a pretty simple model dynamics. It has some nice features that allow to study a kind of easy way. And so it was shown to have a phase transition between, let's say, a state with zero magnetization and a state with a finite SZ. Now, the fact that SZ may be different from zero is not spontaneous symmetry breaking, because the environment tends to flip the spin down. Okay, so it just induces the fact that the average of SZ is different from zero. Now, what is more interesting is what happened in the region where the average magnetization is zero. And this is what you can see, not in the steady state, but in the dynamics. Now, as long as you look at the steady state of a finite system, the only thing you can see is that either SZ is zero or is finite. What is more interesting, just to see how the dynamics develops. And as I said before, just to see this, you have to look at the spectrum of the eigenvalues of the Lindbladians. And you see an example of the spectrum in the two cases. The only important thing is that on the left, you will see that there is a gap. So there is one point at a real part of lambda is equal to zero, which is the steady state at finite n. And then there is a gap with the next eigenvalue with the negative real part. Something which is very much different in the other case, where the spectrum is gapless. So this gap closes with some power law fashion of the number of spins. Has this consequences in the dynamics? Yes. And you can see in the figure that it's about to show, look at the average value of sigma z as a function of time. Now, if you look at the distance, at large times, then you will see that it goes to zero. Okay, but what is important here is not the steady state, but the fact that the decay time, it will increase with the number of spins. So the more spins you put, the slower this oscillation will die out. And they become slower and slower in such a way that if you approach the thermodynamic limits, then you will see that these oscillations will not decay. I remind you that in a spontaneous symmetry breaking, in this, here, the time goes to infinity and n goes to infinity are two limits that do not commute. So if you would take first time to infinity and then n to infinity, then you will always see just sigma z equals zero. But if you do the opposite, then you will see these oscillations. So these oscillations are what what I was mentioning before. These are kind of time crystals with which appears in entirely due to dissipation. And what is more important, as far as I know, the whole class of dissipative time crystal are the only, not only this model, but all the works that have been done are the only cases in which continuous time crystal have been proposed or measured. So in the Hamiltonian case, there are only discrete or Floquet time crystals. So in the next two slides, which I think they are also the last one, I would like to highlight a couple of properties of this model that are related to certain features that one would expect in kind of synchronization. So just imagine, so first of all, there is a kind of proximity effect, which we call kind of crystallization seeding, but in time, in which you can imagine to prepare the system partially in a time crystal phase and partially no time crystal. So these are the two regions A, B, and C, where A has this role of seeding the crystalline phase. If you study the complex dynamics, then you will see that actually, even if at a much smaller level, then you will see that this limit cycle will grow also in region B and C. So, and this is, so if you see in the panel B, then you will see that the region in which this oscillation will appear will spread all through all the system. So in the same way in which you can have a crystallization seed, then you can do something similar here. And something else which I think is interesting is that not only you can have this type of dynamics which induce limit cycle also in region that were outside this region, but also if you prepare two regions that are chosen to be for two different parameters in a non-synchronized form, and you couple them. So for instance, you just take 2D tunings between the splitting of two time crystals, and then you just induce coupled dynamics, then you can observe that in some limit, or better say in some region of the parameter space, then you can induce a synchronized dynamics in the sense that the limit cycle will be locked together. What is interesting, but I have no time to comment on this, is that the synchronization mechanism is very much different from the standard synchronization mechanism, for instance, in Kuramoto or Huygens pendula or things like that. So with this, I have no time to talk about this last part, and just go to the conclusions. And I very briefly introduce the idea of using dissipation to engineering many body state. Then I just present one example of this where I was actively involved in the last few years. That is a dissipative preparation of time crystal. And with this, I think I conclude. Thank you for the attention.
Thanks. Thanks. Very nice talk. So two questions I have. First of all, so this is not a kind of floquet system. So it's not periodically iterated, no? So it's just by dissipation. But can you do that always? Because I can always understand a dissipative process like unitary evolution in a larger Hilbert space. No, I can do this time spring dilation and it's unique. So in this way, did you look what it will be this equivalent unitary evolution?
So this I like a lot, because yeah, the question is the comment is that any dissipative system you can only see as a unitary in a large Hilbert space. So I totally agree. And actually the reason, so we call originally these boundary time crystals exactly because of this reason, because you can always show that you can visualize the thing like the system being at the boundary of a larger system which describes the Hamiltonian of the bus. So And the idea is that it's like, just imagine a cube, okay? In a standard transition, you can have all the magnetization of the bulk, but there are cases in which you have only surface magnetization. Okay, so only the surface is point. And now the analogy is this one. So that you have only the surface, which has a time crystal, and the bulk only provides the dynamics to bring it out of equilibrium. So I think the analogy is really to look at a boundary phenomenon, a critical phenomenon. Yeah. No, nobody likes this, so we stopped talking about this. Yeah. Yeah, so the way to construct the effective Hamiltonian, I don't know. So there are cases in which we use this. So there is a construction. I think at least I learned it by paper from Susanna and Martin, Susanna Welge and Martin Plenio, in which you can show that you have a dissipative system you can describe as kind of interaction with the chain, with long range coupling. So in principle, you can construct this, and this construction is not unique, but yeah.
Thank you very much. Thank you so much for the very nice talk. Towards the end, you were talking about this synchronization that happens in certain parts of the parameter space. Can you discuss a little bit more what needs to be satisfied for this to happen?
So if you take standard synchronization of, for instance, of oscillators, like for instance, a model like Kuramoto modeling, which you have rotators, which are coupled by some interaction and they're dissipative. So you may have a transition between synchronized and non-synchronized dynamics, which is essentially related to the fact that if you have a spread of frequency, which is not too large, then the coupling manage to synchronize the motion. If the spread in frequencies is too large, then you don't have this. Yeah, right, yes. Now here it's different because the coupling is not an Hamiltonian coupling. So if you have a spread in the, just a moment. If you have a spread in the splitting, then this does not imply that a larger, oh, sorry, it takes. So it does not imply that the larger splitting reduce the synchronization. Actually, it happens the opposite. So this x-axis, omega A minus omega B, the x-axis is the difference in splitting. So if you follow the standard logic, you would say that if you have a larger differences, the synchronized region should shrink. Actually, the opposite happens the opposite. So you have a larger synchronized region if the splitting is larger. So this is related to the fact that the splitting, so it's not the only governing, let's say, parameter, because it depends on how robust is the time crystal in each of the region. So you may take regions in which you have very robust time crystals, and then even if the splitting is larger, then this will not play any role. But I should say that this is something I would like to understand better, because I mean, I don't know if it's a generic So let me say, I don't know if it's a generic feature or it's just of this model that, which is very specific.
Thank you for the presentation, Prof. Just want to know if time crystal are some of semiconductor or the group of material that can be called time crystal.
No, so far, I don't think that there are example of, so that's why people did not, at the beginning, did not even think that they could exist. Because they have to, you have to really engineer and construct the dynamics in an artificial way.
Thank you for the wonderful presentation. It's a follow-up to our question. Assuming we succeed in having materials that we can observe those phenomena, is there any advantage it will add to the way we do physics now?
So the true answer, I have no idea. But one can speculate on this. I think it's a very important question. So, for instance, the idea is that, so the good thing for possible practical purposes is the fact that these are very stable oscillations. And even if just introduce defects, imperfections, or whatever, the oscillation will be unchanged. So possible thing that we are exploring is to use it with for clocks or for some kind of self-correcting dynamics. Another possibility would be, for instance, if you use, if you realize heat engine or a thermal machine that need to have a cycle, then you can have this as a working substance to just keep fueling with a very stable cycle. But these are all, you know, ideas. I don't think that there is a concrete advantage at the moment.
So thank you very much, Professor Fazio. So if there's no other question, and I don't see any question online, so let's thank Professor Fazio